That was the best introduction I've ever had. And for the invitation to be here, I'm so excited to be here. My parents actually met at University of Washington in a parking lot somewhere on campus. My mom says that my dad hit on her in the parking lot, but they disagree about that. So anyway, so Seattle holds a special place in their heart, although now they're down in South Texas, and my mom certainly misses Seattle. Okay, so I'll be talking about robust methods for surrogate marker evaluation. This is joint work with Lu Tian at Stanford and Tianchi Kai at Harvard and is supported by NIDDK. So my goals for the talk are going to be to explain the problems and the ideas. So I'm going to talk about the surrogate marker problem, what it is, and the current landscape, and then specifically talk about two issues: heterogeneity in the utility of a surrogate. So this is when a surrogate marker may be useful for some patients, but not for others. And the small sample problem, like how do you even just evaluate a surrogate when you have a small sample? These are things I'm not going to talk about in my talk, but rest assured, they have been done. So for everything I say, all the asymptotic properties and all of those things, we've shown them. They're in the papers. I'll give you the citations. I'm not going to talk about those. Variance estimation, for most of it, we have closed form analytic estimates, although even when we do, we still do some resampling to estimate the variance. Confidence intervals, I'm usually getting a confidence interval for a ratio, so there's like different ways to do it. We have different ways. Simulations, not going to talk at all about simulations or implementation, but I will mention the R packages. There's an R package that goes with every method, so I will mention what the R package is. Okay, so an outline, I'll go through some background describing what is a surrogate marker in the first place and some different frameworks that are available to evaluate a surrogate marker. I'll specifically talk about one of those frameworks, which is the one that I have worked in, which is the proportion of treatment effect explained framework. And within that framework, I will talk about this heterogeneity idea. And then third, I'll talk about the small sample problem and close with some remarks. Okay, so what is a surrogate marker? So a surrogate marker is something that you can use to replace a primary outcome when you're testing for treatment effect. Pretty straightforward. So in the first example, we have a primary outcome such as a heart attack that might take a long time to observe. So this is a clinical trial where you're randomizing patients at baseline to some treatment or intervention, and you're watching them until they have a heart attack. So this might be 1 year, it might be 5 years, it might be 20 years. The idea behind a surrogate marker is using instead something that can be measured earlier, perhaps something measured in the blood, which is why I have the little blood test tube that's measured at an earlier time point T0, so that I can estimate and test for treatment effect at that earlier time point instead of waiting all the way till time T. So in that first example, the surrogate marker would help me make a decision about the treatment effect sooner, right? Decrease my needed length of the trial. In the second example, I would have a surrogate marker. I would be interested in a surrogate marker that is actually measured at the same time as the primary outcome, but is still of interest because it's less expensive or less invasive or less burdensome on the patient. So here, the primary outcome is measured via biopsy, and this is the example that I'll use at the end of the talk, where I have pediatric clinical trial where the primary outcome is measured with a liver biopsy. And the question is whether we can instead use a measure of liver function that is in the blood instead of having the kids have a biopsy at the end of the trial. They have to have a biopsy at the beginning of the trial. So if we can avoid having a repeat biopsy to test for treatment effect, right, that would be great. So here, we're not talking about a surrogate necessarily decreasing the follow-up time or the length of the trial, but certainly decreasing burden on patients. So this is kind of the whole promise of surrogate markers. This is why I have the rainbow with like the pot of gold at the end. So the whole idea is that if we can find surrogate markers, then we can use them in future studies. And test for treatment effect using these surrogate markers and either decrease the follow-up time or decrease the cost or burden. So this would, enable shorter randomized clinical trials in the length example, and just generally accelerate treatment decision-making. So this is the whole point. This is like why we're doing all of this in the first place. So here are some examples. These are all examples in that first case where the primary outcome will take a long time to observe, and I'm considering surrogate markers that are measured earlier. So in the first one, my primary outcome is a diabetes diagnosis. So my treatment of interest would be something that's designed to prevent or delay diabetes diagnosis. But instead of waiting, 5, 10, however many years, I want to look at the treatment effect at an earlier time point, T0, and some potential surrogate markers may be change in hemoglobin A1C from baseline to T0, or change in glucose, or change in BMI. In the second example, the primary outcome is dementia onset. So certainly a case where we generally require a very long follow-up time, depending on your patient population. And some potential surrogate markers of interest would be a brain image or a cognitive score of some kind measured at an earlier time point. And lastly, a lot of the earlier work on surrogate markers was really motivated by HIV research. So here the primary outcome is disease progression, like an AIDS defining event, and the potential surrogate usually is CD4 cell count. So a reasonable question you may have is, can you even get a drug approved based on a surrogate marker, right? And the answer in the US is yes. So the FDA has an accelerated approval program that specifically allows for drugs to be approved based on demonstrated effectiveness on a surrogate marker. But this is how they define a surrogate. So they say a surrogate endpoint is a marker that is not itself a direct measurement of clinical benefit and is either known to predict clinical benefit and could be used for traditional approval, or is reasonably likely to predict clinical benefit and could be used to support the accelerated approval. So it's that second part that we're interested in. And obviously it's not a very statistically fulfilling definition to say that it needs to be reasonably likely to predict clinical benefit. And this is pulled directly from FDA documentation. So here are some examples of drugs that have been approved through the accelerated approval program. So the FDA originally approved Jardiance, which is for people with type 2 diabetes, based on results showing that the drug lowered blood glucose levels, which is a listed surrogate marker for cardiovascular disease among type 2 diabetics. In the FDA, like the FDA has a table of surrogate endpoints. And then 2 years later, it was approved based on results showing that the drug reduced the risk of cardiovascular death. So sort of an example of a success story. The FDA does usually require, even if they approve the drug early based on the effect on a surrogate marker, that you continue the trial to still measure the primary outcome. And it's interesting if you watch the ad for Jardiance, which comes up on like Hulu and Amazon and things like that, unless you don't have commercials. They will advertise both saying like this drug reduces blood glucose and cardiovascular death. So I think it's interesting if you really watch some of these drug commercials that the advertisements will be like advertising for reduction of the surrogate marker. Okay, a not so good example is with the recent drug aducanumab, which you have probably heard about and has been in the news a lot in the past few years. So this was a drug that was approved early based on clinical trial results showing that it reduced visible plaque in the brain, which is considered a surrogate outcome. Again, is in the table, the FDA table of surrogate outcomes. But then the trial showed that it did not have a noticeable effect on patient outcomes. So this has caused a lot of controversy, a lot of discussion about how closely the FDA worked with Biogen, who made the drug, And it has been interesting from a sort of policy perspective to also watch what has been happening with coverage, insurance coverage, and financial aspects. So of course, when this drug was first approved based on the surrogate outcome, right, the stock price shot up for Biogen. And then subsequent results came out showing no effect on patient outcomes, stock price goes down. FDA says, well, they're not going to pull the drug. So that is also a very controversial thing, is there's not really a mechanism in place for FDA to pull a drug that has been approved early based on a surrogate marker when it then doesn't have an effect on the primary outcome. Now, if it killed people, okay, that's different. But if it just doesn't have an effect on the primary outcome, it's not necessarily the case that they're going to pull the drug off the market. So FDA says, well, we're not going to pull the drug. Stock prices go up again. Then Medicare says they're not going to cover it. Technically, they said they're only going to cover it for people who are in a clinical trial. So stock prices go down. Private insurers, most private insurance also follows suit. So it's been very interesting for me to watch this. And then January of this year, Biogen said that they are discontinuing the drug themselves. Okay, so all of that to say, so far, I haven't really given you a very good statistical definition of a surrogate marker, but Ross Prentice gave us exactly that in 1989. So the Prentice criterion that he proposed in this foundational paper on surrogate markers says that a valid surrogate marker should be such that a test for treatment effect on the surrogate marker is also a valid test for the treatment effect on the primary outcome of interest. So that is certainly more statistical than reasonably likely. And while basically every single paper on surrogate markers since 1989 references Ross's paper, there has been a lot of criticism of this paper, and there is really a lack of agreement on a single method to validate a surrogate marker. So there are three frameworks generally for evaluating a surrogate marker. I really like this recent paper by Michael Elliott that came out last year that is a review of these frameworks. He does split up the proportion of treatment effect explained framework and the indirect effects and directs framework. I am combining them here, which not everyone would agree with me, but I'm still doing it. This is what I have worked on the most and what I'll focus on and explain more in the talk. It is also used the most in practice, used very widely. The second framework is principal stratification, which Peter Gilbert has done a lot of work in this department. And he proposed the causal effect predictiveness curve, and this is very much from a more causal perspective. What I will talk about will still sound causally, but I don't really claim that it's a causal inference framework. And then the meta-analytic framework is really the gold standard, even though I said that there is no single method that everyone agrees upon. That's not quite true, because I think that all of us that work in surrogate markers would agree that the meta-analytic setting is the gold standard. It's just that we don't usually have all of these trials to do a meta-analysis. So I usually just have one study. I have one study and I'm trying to evaluate the surrogate in one study. So I don't have the luxury of doing meta-analysis. Okay, questions so far? Like I'm talking a lot. Okay. So let me introduce some notation to talk about the proportion of treatment effect explained framework. I'm assuming throughout I have a randomized study. These are clinical trials. They're usually randomized. Y is the primary outcome. S is the surrogate marker. G is the treatment indicator. Again, randomized, either 0 or 1. And so I have potential outcomes notation. So Y1 is the primary outcome under treatment 1. Y0 is the same thing, S1 and S0. So everybody in my study has these 4 potential outcomes, but of course I only observed the pairing for the group to which they were assigned. So in that Prentice paper, he suggested that a surrogate should be able to capture the dependence of the primary outcome on treatment. So a good surrogate should be able to capture a large proportion of the true treatment effect on the primary outcome. And motivated by this, a lot of work has focused on trying to define and estimate this quantity, the proportion of the treatment effect on the primary outcome explained by the treatment effect on the surrogate marker. To be fair, Ross did not suggest that proportion, but that it really came from his proposal. So that is the whole, what's in blue is the whole phrasing, but I just abbreviate that as proportion of treatment effect explained, because it's just very long to say the whole thing. So Friedman in 1992 proposed this very simple way to define and estimate this proportion. So like you can do it in Excel. Okay, so you fit two regression models. The first is just, right, your outcome is your primary outcome, and you just have only the treatment indicator in the model, and you look at that regression coefficient for treatment. Then you fit a second model where you just throw in the surrogate marker and you see how much your regression coefficient for treatment changed. Easy. And he defined the proportion of treatment effect explained with this RS, R because it's a ratio, 1 minus the ratio between these two regression coefficients for treatment. So if you fit that first model and your regression coefficient for treatment is like very big, and then you fit your second model and now that coefficient is 0, right? It really feels like that surrogate is capturing the treatment effect. If you work out that little 1 minus whatever, you're going to get a proportion of treatment effect explained of 1. On the other hand, if you throw in the surrogate marker and your regression coefficient for treatment does not change at all, your proportion explained would be 0. That surrogate is not capturing anything. So many things wrong with this approach, so many. And many people have criticized this approach, myself included. Nonetheless, it is used all the time, even today. Applied papers use it all the time. Now, just because everyone's doing it doesn't make it right. But I have really focused on this proportion explained quantity because it's very intuitive. It's very appealing. And so I have spent many years trying to estimate this, define this, and estimate this better. But anyway, one of the things that's wrong with it is, of course, these two models have to be correctly specified. In the survival setting, like if you do Cox proportional hazards, you literally can't have these two models holding simultaneously. And very bad things happen when they don't hold. I mean, the definition depends on the models, right? Not just like the estimation, like the definition depends on the model. So when the models aren't correct, it's like not even clear what it is what you're doing. So 10 years later, Wang and Taylor tried to kind of redefine this quantity using a different approach, but still getting at the same idea by trying to capture what the effect of the treatment would be if the values of the surrogate in the treatment group were distributed like those in the control group. So this is where it starts sounding like more causally. They considered a contrast between the actual treatment effect on Y, so that's delta. That's not new information, right? That's just your average treatment effect. Easy to estimate because we have a randomized clinical trial, so I'm allowed to just take the average of Y in the treated group minus the average of Y in the control group. A contrast between that and this idea of the residual treatment effect, which is the hypothetical treatment effect when the distribution of the surrogate under treatment is the same as that under the control. So that looks like this, right? So looking inside the interval, this is just what I said. So the expected difference in the primary outcome between the two groups if the surrogate distributions looked the same in the two groups. This is not saying I'm assuming there are people for whom these are equal. This is a causal quantity. But it's that expected value and then integrated with respect to some reference distribution for the surrogate marker. Here I'm choosing the reference distribution as the distribution of the surrogate in the control group. You can choose the treated group. You can do a pooled combination of the two. It'll change how you interpret the quantity. But I choose the control group because I like the fact that I can think of it as like the leftover treatment effect after you account for the treatment effect on the surrogate, right? So then the proportion of treatment effect explained is still calling it this RS, but it's the delta minus delta S. So if delta is the whole treatment effect and delta S is like this leftover treatment effect after you account for the effect on S, then delta minus delta S is the chunk explained by S divided by delta is your proportion explained. Very parallel to the direct and indirect effects framework that you see in mediation and elsewhere. So notice that this definition at no point had any kind of models involved in the definition, right? Wang and Taylor proposed this whole approach. Their estimation of delta S is model-based. So they propose parametric models where you specify models for Y given S and the treatment group. But those models can be very flexible. You can show that if you specify some very simple models, this RS will equal the Friedman RS. So if there's no interaction and everything's linear and simple and the models hold, they will equal. So this idea of decomposing the treatment effect into two pieces is not new information, right? But it's very intuitive. So you have a piece that's captured by the surrogate, not captured by the surrogate. It's simple to implement, at least certainly the Friedman approach, but even the Wang and Taylor approach, if you use some parametric models, it's not that bad. And again, this single number summary is very appealing and hard to beat. In terms of estimation, like I said, there's very simple parametric estimation, which is the Friedman approach, more flexible parametric estimation, which you can use within the Wang and Taylor approach. And what we proposed was fully non-parametric estimation, which is what I will talk about now. So remember, our delta is just this difference in the primary outcome between the two groups. I can estimate that very easily with the averages. The residual treatment effect is what's a little bit harder to estimate. So that first line is what I already showed you. To get from the first line to the second line, I do need an identifiability assumption, which we could have a whole talk about, and people might argue with me about it. But that's this assumption down here, my identifiability assumption. And that allows me to pull out, right, to pull out the S0 from this term and to pull out the S1 from this term so I can break it up and make them identifiable. And then the last line is just, right, that second term is just by definition. So I'm really just left with that first term on the last line that I have to estimate. But that's really not that hard, right? That expected value is just the conditional mean of Y given S. S is a scalar, Y is a scalar. I'm just going to do Nadaraya-Watson kernel estimator to get the conditional mean of Y given S. Non-parametric, totally fine. I'm going to integrate with respect to the empirical CDF. So I'm going to take that kernel conditional mean estimator that I'm going to estimate in the treated group because that's the expected value of Y1 given S1. And then I'm going to apply it to everybody in the control group. That is the same thing mathematically as the integral with respect to the empirical CDF. And that just looks like this. Okay, so this is robust, right? I don't need any kind of models. Of course, I have to estimate a bandwidth. That's always something I have to do with kernel estimation. But it works pretty well, and it very much beats the parametric approaches when those models don't hold. And this is all implemented in a package on CRAN called R Surrogate. And it has all the things I mentioned earlier that I'm not talking about, variance estimates, confidence intervals, and so on. Can also handle primary outcomes that are censored, survival outcomes, and multiple surrogates. Okay. Questions before I move on to heterogeneity? Okay, so still within this idea of the proportion of treatment effect explained, I want to talk about what heterogeneity means. So most of the evaluation methods really are kind of silent on this idea of heterogeneity, which is when the surrogate can be useful for some patients, but not useful for others, right? Just like treatment effect heterogeneity, we have treatments that, you know, work better for some patients than not for others. But here we're talking about the surrogate's ability to capture the treatment effect being different for different patient populations. So how do we test for heterogeneity in the utility of a surrogate marker? This is especially important if you're talking about using the surrogate in a future trial, which again is the entire point of everything that we're doing, is that we want to identify surrogates so that we can use them in a future trial. But if it's the case that you have a surrogate and let's say it's good, however you define it, my framework or someone else's framework, it's good for older patients, but not so good for younger patients. And it just so happens that your trial, your next study is all younger patients, and you either didn't know about this heterogeneity or you knew about it and you ignored it, and you did use the surrogate marker to replace the primary outcome, right? Bad things could happen. So it's really important. So far I have been talking about the case where I'm in this kind of pink region. So I've been talking about a setting where I have one study and I have the surrogate marker and I have the primary outcome and I'm evaluating the surrogate in my single study. Now in this figure, I'm going to refer to that study as study A. It's my study A where I have the surrogate and I have the primary outcome. And again, our whole goal is to learn about the surrogate there and then conduct a study B, either be designing the study B or it's already done, be able to stop the study B at the time of the surrogate marker measurement and test for a treatment effect there, and then be done with it. Of course, in the FDA, like I said, they still make you continue the trial, but this is the idea. And this tiny little rectangle that I have in the middle that's transportability and design is like a huge other issue that I'm not even talking about today. And it's like an entire grant. But there's a lot that you're assuming when you say that you can validate a surrogate in study B and then use it, in study A and then use it in study B, right? There's a lot you're assuming about transportability. This is going to sound very similar to like domain adaptation and transfer learning. There's a lot we need to assume to go from one to the other. There's also a lot that you can do in terms of designing study B in an optimal way if you know information from study A about the surrogate and you plan to use the surrogate in study B. But at this moment, I'm not interested in the transportability piece necessarily. I'm interested in these baseline covariates and seeing whether there's any evidence of heterogeneity in study A with respect to a baseline covariate, because I would use that information in study B if I actually use the surrogate to test for treatment effect. So what this means is that I need a definition and an estimate of this proportion explained as a function of W, basically, right? Where W is my baseline covariate of interest. So I'm going to assume that W is just a single baseline covariate of interest. Gets a little bit harder when you have multiple baseline covariates. But let's say it's just a single baseline covariate. This delta of W, that's not new, right? That's just treatment effect heterogeneity, that WU. What did I say? Delta W. Delta W is just treatment effect heterogeneity. Delta S of W looks a little bit more complicated, but it's really not. It's just taking that delta S we already had and just conditioning on W everywhere. So that conditional mean that I have in the middle is just now, instead of like your Notter Watson estimator, it's just a two-dimensional kernel smoother, right? If I just have W as one dimension, it doesn't get too bad to do two-dimensional smoothing. I won't go bigger than two-dimensional smoothing, but I can use two-dimensional smoothing there. My CDF is now just, again, conditional on W. I can also do my kernel smoother there and get an estimate of delta S of W fully non-parametrically. And then my RS of W is, again, just that 1 minus the ratio between those two. So we do fully non-parametric estimation here. We do have 3 bandwidths now, so it's complicated to pick the bandwidths, but you got to pick the bandwidths. And we have formal tests for heterogeneity. So we have 2 tests, an omnibus test, which tests across a broad range of alternatives. And then the trend test is basically if you're willing to assume that your RS of W is monotone in W. So if you're willing to restrict your space of alternative hypotheses to monotone functions, then you can use the trend test and you get more power than with the omnibus test. So I'm not going to talk about all the technical stuff, but these R packages implement all of this. So the het-sur package will estimate the RS of W as a function of W and like plot it as a function of W. It also does both tests within that het-sur package. The het test package allows you to test in study B using the heterogeneity information from study A. So I didn't really talk about that, but since I gave that picture, I thought I should also give that R package. Questions on that before I move? Okay. In my department, people ask a lot of questions like during the seminar. Daniela, you saw that. So I just feel like I got to pause to check. Okay, so the problem with everything that I've talked about so far is that obviously I said kernel like a lot of times. So you can't do it if you have a small sample size. None of it works if you have a small sample size. And by small sample size, I mean like 25 versus 30, or maybe even 50 versus 50. You cannot do two-dimensional smoothing, or really even just the Naderai-Watson estimator just dies with like 50. So that, let me also say that up until now in the talk, I've kind of been presenting these methods as like, they're all done, they're like tied up with a bow, here they are, they're all so perfect and wonderful, you know. And now I'm gonna do the total opposite, and I'm gonna describe this small sample idea more in the way of like how I got there. And it is very new work, but hopefully you get a kick out of it. So in the past couple of years, I just was getting very annoyed with myself that nothing that I came up with could work with small samples. So the small sample clinical trials are the ones that really desperately need surrogate markers, right? Like the pediatric clinical trials, the trials of rare diseases. These are small trials and they really need surrogates. And I really was bothered by the fact that like I was doing nothing for those. So there's no robust method that I know of that you can use to evaluate a surrogate marker. And I had this data set, which I'm going to talk about in a second. And I just felt like I couldn't go back to, I couldn't use like the Friedman approach after I spent years criticizing it, you know, and I know that it doesn't perform well if the models don't hold. So the trial that I was particularly interested in was this small study of children with non-alcoholic fatty liver disease. It's called the TONIC trial. And they randomized children with NAFLD to vitamin E, metformin, or placebo and followed them for 96 weeks. The primary outcome is that it's called the NAFLD activity score. It's measured via biopsy, and it combines all this information on things that can't pronounce, but like buildup of fat in the liver and lobular inflammation. And the potential surrogate is ALT, which is measured in the blood. And this is an enzyme concentrated primarily in the liver, which increases when there's liver damage. So the groups that I'm going to compare are the vitamin E group, which is 50, and the placebo group, which is 46. So this is exactly the picture that I showed in the beginning, where the primary outcome and the surrogate are measured at the same time, but the surrogate is much less invasive than the primary outcome. And so the question is ALT a surrogate marker for the NAFLD activity score measured via biopsy? So basically, I came to the point where I decided I probably have to give up on the proportion of treatment effect, not give up completely, but give up on this proportion of treatment effect explained quantity, because first of all, a ratio is it misbehaves, right? Ratios are very difficult. So it kind of misbehaves even with a pretty decent sample size. And I just figured with a small sample size, there really was not going to be any hope in estimating a ratio. And then I also just thought, probably we can't really estimate anything, like any point estimate that's that single number summary. But I went back to Ross's like original criterion and started to think about like, what do I really want, right? I want some method that's going to tell me whether if I test for the treatment effect on the surrogate, is it going to tell me the same thing as if I had tested for a treatment effect on the primary outcome? That's it. Like, would it tell me the same thing? Would I come to the same conclusion? So I literally drew out these little bubbles on a paper at home. And I started to think like, okay, let's say I have my Y's and I have my S's, right? Primary outcome, surrogate. And let's say I ranked my Y's and I ranked my S's, and the orange color is treated and the green color is control. Now, if I saw something like this, I would want whatever method I came up with to say, this looks like a good surrogate, right? Like the treatment groups are separated in the Y's. There seems to be a treatment effect if I look at the Y's. There also seems to be a treatment effect if I look at the S's. This is just where I started. Like I want something that would say, probably a good surrogate. And I would also want a method that looks at this and says, like, kind of like, it's a pretty good surrogate. A little bit of stuff here on the S's, but like still pretty good. And then I'd want a method that says, this is not a good surrogate. It's a useless surrogate. That's where I started. And of course, this idea of just ranking, and you have a 2-sample test. This is just the Wilcoxon rank sum test, right? It's not that new information. But I wrote out all these bubbles and I was like, I think this is just going back to like the beginning of graduate school where I learned about the Wilcoxon rank sum test and used statistics. And I had a heck of a good time going back to those papers from the 30s and reading all those used statistics papers and like the Kendall's Tau paper. You really don't see papers like that anymore where they're like, I took all these numbers and I counted how many were above and then below, and then I did it for all, and then I summed them, and then I did it a different way. I came up with the same thing. I'm like, I think there's something here. Let's prove some stuff about it. And then the proofs are like by induction. Like you never see those anymore. If you haven't read those or it's been a while, I suggest you go back. They're pretty fun. But anyway, we're just doing the Wilcoxon rank sum test. So I thought about basically defining our treatment effect quantity. I'm not talking about deltas anymore, right? I'm going to define my treatment effect quantity as the probability that Y1 is greater than Y0. So my null hypothesis of no treatment effect on Y is that UY is equal to half. I'm just going to estimate this with my U statistic, right? Should look very familiar. And then I'm also going to consider doing all the same stuff with the S's. And my question is, does US tell me something about UI? And basically, is US close to UI? That's what I was trying to get at in the beginning. Is my treatment effect on S telling me the same thing? I'm putting that in air quotes as the treatment effect on Y. So that's what I did. I just took the difference between those two. So I defined this little delta that's UI minus US. And I basically want this delta to be bounded by some upper bound epsilon. We're going to talk about epsilon, but let's just say it's something small. So there's nothing that says that US has to be lower than UI, right? Like US could be greater than UI. But I don't want US to be much lower than UI. If it's much lower than UI, then it is not close enough to UI for me to think that it's going to tell me the same thing about the treatment effect as Y. So we considered this non-inferiority test where H0 star is reflecting a poor surrogate. So delta is too big. It's bigger than this epsilon. US is too far away from UI. Versus this alternative where the alternative reflects a valid surrogate, where delta is less than that sort of tolerance level of epsilon. So US is close enough to UI for me to find it tolerable. And all the theory behind this, like I'm not saying it's easy, but it's just use statistics theory. And note that these are two dependent use statistics, right? Obviously the Y's and the S's are coming from the same people, so you can't pretend they're not. This is also the same thing as the difference between two AUC curves, which is kind of fun. So yeah, so you can work out like all the variance estimates, confidence intervals, and things like that from use statistics theory. But let's talk about the choice of epsilon. So there's not really an obvious choice of epsilon. You could consider some pre-specified value, of course. In practice, the choice of epsilon is probably going to depend on a lot of stuff that's not necessarily statistical. the cost of a primary outcome, surrogate marker, potential follow-up time reduction, things like that. But let's think about an approach for selecting epsilon if you didn't have any of these things. So to select epsilon, we basically wanted an approach that would target the power of a test based on US. So I want S to be such that we'd have some level of power to detect a treatment effect on S. So it's kind of like saying, I'm willing to consider you, surrogate, as adequate, even if you're kind of far away from UY, as long as you give me this minimum power that I need. So you can write out what this value U star would be to get you the power that you want. And so this U star would be the minimum value of US, so that such that you'd have this minimum power to detect a treatment effect on S. So you define your epsilon as the max of 0 and UY minus US star. So again, willing to take S as a substitute for Y if it's within a certain like tolerated threshold where I've defined that threshold based on desired power. So this is just one way that we sort of made up to select epsilon. I'm sure there are other ways and probably some optimal ways, but this is one way that we came up with. So let's look at it in the tonic trial. So in the tonic trial, again, our surrogate is change in ALT from baseline to 96 weeks. My outcome is change in NAFLD activity score, also from baseline to 96 weeks. UY hat is 0.655, US hat is 0.550. So US hat, not very good, right? 0.5 is, right, that's our null. My delta hat is 0.105. So that's just the difference between those two again. And the upper bound of that confidence interval is 0.213. So if I assume a desired power of 0.7, this with the method I just described gives me an epsilon of 0.008. So my tolerance is very low, right? I'm not going to tolerate US being very far from UY. And so since this upper bound of the confidence interval is most certainly above this epsilon, I don't have sufficient evidence to support change in ALT as a surrogate marker for change in NAFLD activity score. So this is one non-parametric solution for the small sample problem. I'm still thinking about ways to improve this. This just came out. But we know it had, like, we don't have great power, right? I mean, I can't make magic happen. I have a small sample size. So I have limited power, but it is at least a non-parametric approach. And I just really love rank-based stuff. So I'm happy it seemed to have worked out. We have an R package that implements it all, surrogate rank, which is on CRAN. So just to close up, but still related to small samples. So I think some open problems of many in surrogate markers is combining these two things I talked about, which is how do you look at heterogeneity with a small sample? Maybe it's impossible. I don't know. People tell me that's probably impossible. But I went through this whole spiel about how important heterogeneity is. And now I have this small sample approach. So I'd really love to be able to do something to look at heterogeneity with a small sample. Maybe we can leverage like external data. There's a lot of things going on with surrogate markers. That's like, how can you bring in observational data that you can leverage to help you validate surrogate markers? And like I mentioned, I do have limited power, just even not in the heterogeneity settings. So we are thinking about leveraging baseline covariates like through augmentation to try to gain some power. Also looking at when you have, so right now we have Ebola vaccine data where the sample sizes are, again, very small. And the surrogates are like these, I don't work on genetic stuff, but it's like gene expression, things like thousands of gene expressions. And they want to use this rank-based approach to like screen through all the surrogates and identify the best ones. So I'm very interested in figuring out how to do that appropriately. So Some limitations, I mentioned the identifiability assumption, which is the big one. It's not unique to me. Everyone's going to need an identifiability assumption in surrogate marker work. But there are also some other assumptions that I need that I didn't discuss. I have them in a backup slide if you're interested in. Again, not unique to my approach. So Tyler Vanderweel has this really good 2013 paper in biometrics. It's a good paper, but it's like a sad paper because he goes through all of the surrogate evaluation methods and just like breaks every single one of them. And basically you need certain assumptions to protect you against the surrogate paradox situation, which is when the treatment has a positive effect on the surrogate and the primary outcome are positively associated, but then the treatment negatively affects the primary outcome. Or you can replace all those directions, in the opposite way. But this has happened many times and it's very, very bad. So that's not just saying that the treatment has no effect on the primary outcome, right? It has a negative effect. It's like going to kill people in these arrhythmia drugs. The arrhythmia drugs are the biggest example of that, and killed like 50,000 people. So I need some assumptions. For example, one of them is like that conditional mean of y given S is monotone with respect to S. They are testable empirically, I mean, sort of, but you can do some empirical validation to an extent. There's also the transportability piece, which I glossed over and is a whole separate thing, but is a huge issue. And a lot of people, ourselves including, are working on that. And lastly, it can, I was talking to Peter about this earlier, but it can really get to this point where you feel, it's easy to get to this point where you feel like, is it really worth it? And I feel like this picture here, because there's so many assumptions that we have to make, or you have to do parametric assumptions, or you have to do both. And there are articles coming out all the time. There's just one that came out in JAMA that was like, we shouldn't be using surrogates, like surrogates are making us make all these wrong decisions. There's no good evidence for surrogates. So it can feel kind of like depressing. But the thing is that you can't just say like, don't use surrogates, right? Like people are using surrogates. People aren't going to wait 20 years for a new drug. They want their new drug like yesterday. And so I think that the best we can do is try to give them the best tools possible and acknowledge what the limitations are, what are the assumptions we're making, even if they are really big assumptions and we don't know how to test them. Okay, that's it. Thank you very much. Yeah.
I have a question in terms of, great job. I have a question in terms of like the framing, because I don't know a lot about surrogate evaluation. So is the idea that like a study is done to assess how good a surrogate is for the outcome, or is that like a byproduct of the study that's being done?
It's usually a byproduct, but there was just a paper that came, I don't know if it was JAMA, but it was like some clinical paper that was basically advocating for like, we need to do trials specifically for the purpose of surrogate validation. But that's kind of a new push. It's usually a byproduct.
And then if you, I'm sorry that I don't hear my presentation from the beginning of the talk, but you had like Y1 and Y0 for like whether the person was in the treatment or the response to the treatment. So then if the setting of the trial changes, then the efficacy of the surrogate, efficacy I'm sure is the wrong word, the proportion of treatment effect explained by the surrogate for the outcome would change. Like
is it like if the treatment's different?
No, I mean if the like the thing you're testing, like drug versus, oh yes, treatment, that's the
treatment.
Sorry, this is not my area. Treatment is the word I was looking for, thanks.
Yeah, so usually when you the very rigorous answer is that when a surrogate is validated, it's validated for a specific outcome and for a specific treatment. Yeah, so you have to pair it with the treatment. In reality, people don't like the surrogate table that the FDA has. They don't give a treatment. They're just like, this is a surrogate for diabetes. So in practice, that's a little bit more wishy-washy, but it really does matter, right? It depends if it's a treatment that's like, okay, so like Amgen had this big bone density drug, and they just wanted to take the pill and stamp a picture of a bone on it, like just a bone, like an outline of the dog bone. and then they needed to test better. So like, that's the same treatment, but the FDA gets very mad about that because it does change I don't know about how this all works, but like, if you stamp a pill, it changes the composition of the pill. So you can't just say, oh, this will definitely have the same effect. But like, if you had a surrogate that was a surrogate for that first pill, like this probably would be a surrogate for the second pill. If you have a lifestyle intervention in one trial and then you do another lifestyle intervention and it's basically the same, like at what point are two treatments very, very different? If the treatment mechanism is like, it's different biologically, you really can't call that a surrogate for the same thing.
And then okay, thanks for that. So then if you identify a surrogate, like or if you validate a surrogate as a byproduct of a different trial, it's actually like for the outcome, then can you, on that same trial, use that surrogate you need now a new trial?
Yeah. And so some people will, you need a new trial. And so some responses to that will be like, well, why would I do a whole nother trial if I just did a trial that's like the same, that treatment and that outcome? And now you're saying this is a surrogate only for that treatment and that outcome. Why would I do a whole nother trial? People do it all the time. You get two different drugs, two competitor drugs, different populations. Phase 1, phase 2 trial. Phase 2, phase 3 trials. Good. Yeah.
Please comment on the difference of similarity between that residual between the path versus just the usual method interactive factor calculation analysis, and also because it seems to me that thing you're looking for is just a principal effect, which is a principal thing.
Yeah. So there's some good papers, not by me, but Anna Conlon, she was one of Michael Elliott's students. I think it's her. She has a really good paper where she does exactly what you're saying. And she puts side by side the PTE, the direct and indirect effects framework. And you know what? I always get confused with like, all the terminology with like the natural and the controlled and the direct. I'm not going to pretend like I am going to be able to repeat that now. Every time I read it, I'm like, oh yeah, I get it. One you can manipulate, one you can't. I get it, but I can't remember. Anyway, so she does PTE, direct effects and indirect effects, and then the principal stratification, and writes out like what pieces of these are equal, and when are they equal? Like under what conditions are they equal, and under what conditions are they not equal? What I haven't seen anyone do, I know this part is not what you're asking, but what I haven't seen anyone do is actually take a data set and like do both. And I've been on my list for like 5 years, but I haven't done it because I didn't have any grad students, but now I do. Like take a data set. Well, I didn't do, but like I have a big diabetes data set. And what if I just applied like my PTE, non-parametric thing, and then did like Peter Gilbert's, causal effect predictiveness curve. I think some of his earlier work was like the constant biomarker situation, which I most certainly don't have. So that's where your control group is the same, like has the S is the same for everyone in your control group because it's like a vaccine study. So I don't, which makes it easier in principal stratification, but actually like I can't use my method at all if there's no variation in the S in the control group. But anyway, I haven't seen anybody do that. And I'd love to see someone do that because in reality, like they should tell, if one method says it's a good surrogate, you hope the other one says it's a good surrogate as well. And if they don't agree, like something's wrong. Yeah.
Just in general, sometimes we also, sometimes we just collect biomarkers. If those short-term biomarkers can predict an long-term endpoint, you can do some pure statistical prediction. I can just report the how good is or collectively predictors. You don't have to resort to the proportion mediated, which relies on how the subject is.
Yeah.
Why don't we just go back to the same point?
Yeah, that's a good question. Because what you said has nothing to do with treatment, right? So just saying which biomarkers are predictive of this outcome, that's not actually what I care about. Like I could have a marker that's predictive of the outcome, But if it's not capturing the treatment effect on the outcome, then it's useless to me. It could be very predictive, but I care about whether it can capture the treatment effect. And that's not the same, that's not necessarily the same thing. So that's like a predictor is not a surrogate necessarily.
Right, but if we found about saying that also invested to verify the neutralization antibody markers, and I know those maps predict my long-term. So then, I think it's pretty, seems reasonable to just say that I'm not.
Well, there are papers that would disagree with that. Yeah, so I think the vaccine setting is a little bit, again, easier in some ways, harder in others, but easier in a way that like, and I'm not an expert in vaccines, but like, it can like literally only affect one pathway or whatever the word is. So if you see an effect, it has to have been through that pathway. Usually in things outside of vaccines, that's not the case. But yeah, it's not necessarily the case that if something is highly predictive, it's going to be a good surrogate. Yeah. Yeah. Mm-hmm.
Yeah, that's excellent talk, very, very clear. And I have several questions, but just ask one. So why do you choose use statistics for the small sample? Because textbook use statistics theory is still asymptotic inference.
Mm-hmm.
I mean, if you for small sample, I would say, for example, we can try a small sample like randomization. That gives exact p-values. So is that what you do for the use statistics?
That's not what I do, but that's like a randomization test.
Yeah.
Yeah. No, but that's on the list. Okay, I haven't done that. Yeah. But that would be really good. Okay, you look like you want to ask more. So I feel okay.
So does the field study also the timing of the surrogate kicking in? Because I would imagine if a surrogate, let's say 2 years out, was not ineffective, would someone be like, you just measured it 6 months too early? I bet on my doubloons that if you just measure it 6 months later, then it'll be a very effective surrogate. And then would that trigger like a whole nother study, or like are there methods that can do people longitudinally measure the biomarker to figure out what time should I measure this surrogate? Or
yeah, so that's a really good question. So we've done that. We have a paper that's estimating this proportion of treatment effect explained for a longitudinal surrogate. So in the diabetes clinical trial, which I didn't talk about, but most of the work I've done before this was motivated, it's the diabetes prevention program. They have the blood glucose, well, they have lots of surrogates measured every 6 months. And so the question is not necessarily, does the change in glucose, at 2 years, is that a good surrogate? It's like, is the longitudinal trajectory a good surrogate? And when you look at, and second question, looking at that longitudinal trajectory, can you identify the optimal time point, the optimal earliest time point, such that that PTE is at some level that you deem appropriate? Yeah.
There are no more questions. Thanks, Layla, again.
Thank you, guys.